the value of the transfer functions of the first order system, so we can only change this slope, right? Okay, this is in time domain. So we see the system is stable because the fact that if we see that this is e to the minus 10t, so the system will be stable, and then the root for these systems is negative, is on the left hand plane. All right, so now we want to see whether the system is, to prove that the system is also stable, if we see the systems in term of in a S domain, right? So this is in time domain. So let's see the system in time domain. Let's say based on that, the systems, right? S plus 10. So we need to find the roots of the systems, which is roots of CE equal to S minus 10, right? That is the root. Okay, then we plot on the S plane, right? On the S plane here, and then narrate. Okay, this is S plane, and then okay, this is minus 10. Okay, right, minus 10. Okay, based on this, we know that from the stability criterions, we know that if the roots of the denominator of systems is on the left hand plane, all right? So we can say the system is stable. Let's say, okay. Okay. So in any future system, we don't have to prove in the time domain. We can simply say that if any roots of its denominator, it's on the left hand plane, then we can simply say the system is stable, right? So you can say that since the root of the denominator of the system is on the left side, the system is stable. Okay, and again, if we increase that, okay, if we change the value of the root, that means as, let's say, maybe we can change to g of s to 1s plus 1 or 1 plus 100, s plus 100. Okay, it turns out that our s is equal to minus 1, s equal to minus 100. Okay, it will only change the locations of the roots along this. Right? Okay. So for first order system, right? For first order systems, we only have one type of response. So the response is like this. Okay. The response is like this. Once again, we have one response, right? Like this, the response. So okay, you see that? So if we change that the transfer functions, no matter how we change it, okay, the roots actually moving along this line, right? And then eventually it will only change the shape of the slopes here, right? So that is for the first order systems. Okay, only one type of system. In first order systems, the response is overdamped. Okay. For first order system, the response, the output, the response can only be overdamped system. Okay, overdamped systems. Okay, only one type of systems, overdamped systems, right? So, all right, probably we can do one exercise. Okay, let's refer to the slides. Okay, before that. Okay, you see that the yellow color, right? The yellow color is the inputs 1 over S to the systems. The black color is the response, the output response. You will see that the output will take some times after the input is given to the system, to supply to the system, right? So that response depends on the system, the system itself. The values and the parameter of the system itself. If we change the value, the shape of the response will change accordingly, right? From that response, we can determine the parameter. So there are how many parameters? There are 3 parameters for the first order system. So the first one is time constant. Second is rise times. Rise times we measure time taken from the response rate 10% to 90%, not 0.1%. That's a mistake, typo there. So 10% to 90% of its final state outputs, that is a rise time. Settling times is time taken for the output response to reach 98% of its final state. All right. So they will discuss this later in the first order response analysis. And then for time being, just understand how we determine the stability and how to find the roots and plot it on the S-plane and so on. Okay, let's do some exercise here. Find the roots. Okay, based on the positions of the roots, determine the system stability. Okay, as simple as that, right? So can do some exercise here, and then we continue to the next series, which is second order and higher order system.